Of a 0.33 molar cobalt Roman numeral 2 chloride solution. How do we make the solution? How's our special friend?
Okay, same.
We might want to know how to make a solution. And a problem could ask you, could you make 100.0 milliliters of a 0.333 molar cobalt 2 chloride solution? So how on earth are we going to solve this problem? Let's go over here and take a look. We know that molarity equals moles over liters at this point. We're still going to write it down. We're now going to put the numbers in as 0.333 molar equals X moles, that's our unknown, and we're going to convert 100 milliliters to 0.1 liters. We're going to solve for X. X is now 0.0333 moles of cobalt 2 chloride. Aha! We also wrote down the formula COCl2, which is a formula of cobalt chloride. We're going to go one more step and take moles and convert it over to grams. 0.0333 moles. We have to figure out the molar mass of cobalt chloride. We figured that out over there. It's 129.8. Moles go on the bottom, grams go on the top. And we get 4.32 grams as to our amount of cobalt chloride we need to add. So now what do? We put on our goggles. We're going to take a balance and weigh out exactly 4.32 grams of cobalt chloride. The cobalt chloride is a nice purplish color. We're going to take a special piece of equipment called a volumetric flask. Volumetric flask measures only one volume, and that's 100 milliliters. We can have a larger volumetric flask that would measure exactly one volume, 250 milliliters. This one is exactly 100 milliliters. You won't see it, but there's a tiny line right here that lines up exactly where 100 milliliters is. So, here's our 4.32 grams. We're not going to add 100 milliliters of water. We're going to add 100 milliliters of solution. So notice, I'm just going to pour some water in. Do I measure it? No. And now I'm going to very carefully pour in our 4.32 grams of cobalt chloride. And we're almost done. We usually fill it only halfway. That way we can do a really good stir. So we're stirring it, making sure we try to dissolve as much of the cobalt chloride as possible. And then we're going to continue to add a little more water until we're almost to the top of the 100 milliliters. Notice again, we're not measuring exactly 100 milliliters. The chemical and the water together will make 100 milliliters. When we get close to the top, we're going to go ahead and use the spray bottle to try to measure out when we're exactly at 100 milliliters. So we're going to keep adding it until we're almost at that spot. We're going to go ahead and look and measure right from the meniscus. We're almost there, and a little tiny bit more, we're there. So this is exactly a 0.33 molar concentration, and we have exactly 100 milliliters of total solution. So in gas laws, there's a lot of fun things that can happen. One of my personal favorites is the Cartesian diver, for which if we look very closely at this Mountain Dew bottle, which was delicious, it's filled up with water, and inside of there was a test tube. The test tube was flipped upside down, and there's a rubber stopper on top of the test tube. The rubber stopper has a hole inside of it, allowing water to either come out or come back in. Now we've trapped a little bit of air inside the test tube that you might be able to see inside of here. And with some magic, we can go ahead and sink this test tube. So if one of my favorite students in the back would go ahead and just simply say, sink, sink, sink.
Sink, sink, sink.
Then it magically sinks. And then if they were to ask it to rise, then it slowly rises. Wow. Are we magic? No. We're not. We're scientists. If we look very closely, the amount of gas trapped inside of there is maybe this much. When we squeeze really hard, the water goes up into the test tube. And now the volume of the gas is compacted. If I have a smaller volume of gas, that means my density is going to be bigger. Can you think about why that's going to happen? Smaller volume and density equals mass divided by volume. I'm dividing by a smaller number. This gives me a bigger density. If it's a bigger density, it will sink in the water. And when I release again, the water escapes out of the hole and the density of this Cartesian diver now rises. So here we have an ordinary balloon, but the balloon is inside of a bottle. So this demonstration is called balloon in a bottle. So in this case, we're simply going to try to blow up a balloon. And we blow it up and it blows right back. In this bottle, there's a small hole on the bottom. So what we're going to do is we're going to take a rubber stopper and plug the hole. Then we try to blow up the balloon. The balloon does not blow up. Why doesn't it blow up? Well, there must be something inside of this bottle. We call that thing air. And air exerts a pressure, and it's stronger than my exhaled breath. Now here's a fun one. Let's blow up the balloon. Aha! I blew up the balloon, pushing the air out, and then I put the cork in afterwards, and now our balloon is inflated, even though it's not tied. That's fun. So, in here we simply have a meter stick. Nothing special about the meter stick, an ordinary meter stick. And on our table we simply have newspaper. And it's maybe 3 or 4 sheets of newspaper. I can lift the newspaper up. I'm going to slide the meter stick inside of here. If I was to practice karate and karate chopping, I might chop this in half. But if I chop this in half, something is going to have to be on this end to hold this end down while I chop. Well, we have that thing today, and it's air. And air pushes down with a weight of about 15 pounds per 1 square inch. And then another square inch, another 15 pounds. So the weight of the air is going to hold this end down while I try to chop this. Now, it's a little bit tricky because the weight of the air has to be on the bottom, but between the paper and the desk, there has to be no air. So I carefully try to push out all of the air that's between the desk and the newspaper. So there's only the weight of the air pushing down. Are we ready? 1, 2.
Nice.
So in this demonstration, we're going to go and do the wet paper trick. I have regular paper. It's dry. We're going to take this dry paper, crumple it up, it could be homework, and stick it to the bottom of this ordinary beaker. We're going to invert the beaker, and we're going to take this beaker and put it into another beaker filled up with water. We're going to push it down, 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 all the way and submerge it well below the level of the water. Then we're going to lift it up, 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 and we're going to take out this wet piece of paper because it was all the way at the bottom, and we realize it's dry. So what on earth is going on here? This, to me, is a great demonstration that air takes up space, and it does have volume. So here today we have a syringe, and this is a classic demonstration of Boyle's law. We're going to fill up this syringe with approximately 60 cc's, or 60 centimeters cubed, or 60 milliliters of air. Now we could fill this up with any gas, helium, hydrogen, nitrogen, carbon dioxide, any gas will work. And as we decrease the volume of this syringe, the pressure will build up. Now on the other end of this syringe, I've melted it. It's all sealed up. So how many air molecules are in there? However many molecules are in there now are the same number of molecules, but they're squeezed in close together. The pressure will build up. If I start at 60 milliliters, and if I squeeze it down to 30 milliliters, I'll feel twice the pressure. If I squeeze it down to 15 milliliters, I'll feel 4 times the pressure. If you try to squeeze any more, you won't be able to, because we're limited by how strong we are. This is a classic example of Boyle's law. Robert Boyle said that if you take the pressure values, which we don't have, but we can go ahead and calculate, multiply them by the volume values, you will always get the same number again and again and again. The number of molecules trapped inside have to stay constant, and the temperature have to stay constant as well for Boyle's law. So here we have what are called fender pullers. There's some other names for them as well. They're devices that when pushed together will make a really good seal. So inside, between these two fender pullers, there's no air at all between them. On the outside, there is air pushing this way, there is air pushing this way. So if we take these two and try to separate them, we're going to have a tough time. We'll try that again. Push them really tight together, make sure we've got a really good seal. The key is we want to have no air in between them, and if we pull really hard, it's almost impossible to pull them apart. If we crack them open and let air in there, it's very easy to separate them. You might see why this is called a fender puller. If you get into an accident when you're 16 years old driving and you bump the car, you can stick this on to the fender of where you got into an accident, get a really good seal, and pull really hard, and your mom will never know. So here we have an ordinary can in which there's a hole and it's filled with water. So if I look at the hole really carefully, the water should be coming out, and it's not coming out. That seems sort of strange. But again, we can command it to come out from our favorite student in the back.
Come out.
And then she can tell us to stop.
Stop. Out. Stop. Out. Stop.
So she's pretty good, isn't she? But it's not magic. On the other side of the can, there's another hole. And this other hole, when I let go, the air rushed in and the water left. If the air doesn't rush in, then the water can't leave. Let's just pretend that the water left and no air came in. What would we make? We'd make a vacuum. We know Mother Nature doesn't like those. Enjoy.